Hi guys, Matt here. Today I'm going to be presenting a video about sample size determination. And most of this stuff came from Wikipedia or the powerandsamplesize.com. And I'm almost positive there's an error on Wikipedia under, what section is it? Under the estimation section. The first example is definitely not correct. So if anyone could verify that it's not correct, that would be great, because then I'll fix it. So what is sample size determination? Why do we care? When would you use it? Whatever. So sample size determination is to choose the number of observations or replicates to include in a statistical sample. That's sort of, in practice, it is calculated to find the minimum required sample size with sufficient power for some measurement or test that you're running. And so basically it's the minimum number of samples to show strong evidence that there is in fact a difference in two means of some value, or the margin of error for the confidence interval for something such as a proportion is less than plus or minus 3%, something like that. And so there's several different ways to determine a sample size. The first way is based off of experience or convenience or practicality. This is not mathematically sound, but sometimes for practical reasons you can only get so many samples. Or based off of experience, you did a similar study and the difference between this new study you're designing and the last one isn't much, so you think you can use the same sample size. But more mathematically sound ways are to have a target variance or a margin of error that you want your estimate to be within, or a target power such as you want to be 80% confident that you'll conclude the alternate if the alternate is true, something like that. Some really basic concepts are that a larger sample size will lead to better precision in the estimates of your parameters, though that is not necessarily true, given, according to Wikipedia, if you have garbage data, then increasing the sample size won't fix your problem. Your problem is probably a systematic error or a dependence problem or possibly a skewed distribution. But anyways, if you have systematic errors, increasing the sample size will help. Just a side note. So I'm going to draw a picture, and then I'm going to talk about sample size estimate for the mean. Then I'm going to talk about the sample size estimate for a hypothesis test. And then I'm going to talk about the sample size estimate for stratified random samples. So you have some data. So for the means, sample size estimate for the means. Sample size estimate for the population mean. So you have some data, follows some distribution, whatever, and then the mean. I should use different colors. The mean, by the central limit theorem, the mean is going to be normally distributed, or almost approximately normally distributed. And so the mean will follow some normal distribution. Pretend that's a normal bell curve. And so this is the mean. And then intuitively, the more we sample, the less variance we'll have. So it'll be something like that. So if we calculate a 95% confidence interval for this last one, it'd be like this. But if we take a bunch more samples and calculate the confidence interval, it'll be like this. So if we have more samples, the interval will be smaller than if we have very few samples. That's sort of intuitive. And then that it should be centered about the true population mean due to the law of large numbers. So the more you sample, the closer to the true mean its expected value becomes. And it's normally distributed by the central limit theorem. So moving on to sample size estimate for the means. I'm gonna erase this. Alright, and for means. So, since the mean is normally distributed, the estimate for the mu and your cot mu hat is at least approximately normal to follow the true mean, and the variance is going to be sigma over square root n. So the more samples you have, the smaller the variance. A 95% confidence interval for the mean would be, we're going to derive the sample size formula from the 95% confidence interval. 95% confidence interval for mu would be based off of x bar. The average is x bar plus or minus, is basically x bar plus or minus 2 standard deviations. That's approximate. It'll be x bar minus 2 sigma over root n, and x bar plus 2 sigma divided by root n. So the mean, the sample average minus 2 standard deviations and plus. So now the width of this confidence interval, we draw it, we're going to have, so this is mu 2 sigma, 2 sigma. So then the width of this interval, so we have an interval. Now if we calculate the width of it, should be pretty straightforward. It would be x bar plus 2 sigma over root n minus x bar minus 2 sigma over root n. So this point, subtract this point, x bars cancel, and that's equal to 4 sigma over root n. So if I could, I screwed that up. So it makes sense if we have 2 units from the mean in each direction, the width would be 4 units. So if we solve this for n, solving for n, that yields n is equal to 16 sigma squared over w squared. Okay, so we just solved this formula in terms of a variance or a width, which is essentially the target variance or target standard deviation. So if we pre-specify a width that we want, it's pretty common to say you want to be confident within plus or minus some value. If you're looking at polling right now, because the election's going on, a lot of times they want the margin of error plus or minus 3%. So it'll be some value plus or minus 3%. We put 0.03 in here for 3%. You can calculate the sample size. We do it plus or minus 10% just for ease of calculation, and the variance was 0.25. Oh, that would be nasty. So anyways, that's the sample size formula for a mean if it's normally distributed. And now let's move on to hypothesis testing. So and for hypothesis test. So for a hypothesis test, it gets a little bit more complicated. I'll draw a picture. So we have alpha and beta and 1 minus beta and all sorts of stuff going on. So we have the distribution under the null, which is H naught. So under the null, it has the mean H mu0 and some variance. And under the alternate, it has a mean that's not equal to the null, and it has the same variance. And we have beta. So under the null, alpha is the probability of rejecting the null when the null is true. And beta is, under the alternate, is the probability of failing to reject the null when the alternate is true. So we define a location C as the critical value. So if the observed sample mean exceeds some critical value C, then we reject the null and we conclude the alternate. And if it's less than C, then we fail to reject the null. So then that creates two regions. If it's less than C, it's called the acceptance region. So I'll just write accept. And if it's greater than C, some value C, this is the rejection region. So then we can, so alpha, this alpha right here, which is usually 0.05%, is defined as the probability that the observed test statistic, which is just the sample mean. My notation's a little clunky. That x bar, let's just do x bar, is greater than or equal to the critical value C given the null's true. So if the null's true, usually this is 0.05%. And mathematically that's equal to 1 minus phi, the critical value minus the mean under the null divided by sigma over root n. And we can solve this for the critical value. Solve for the critical value that you'll see is equal to mu0 plus z of 1 minus alpha times sigma over root n. That's multiplication symbol. So this is just the mean under the null plus 2 standard deviations from the mean. That's all that is. Sigma times the z value is usually 2. So that's what alpha is. Now we're going to derive what the power is equal to, then run a sample size calculation based off of the power. So now the power is equal to the, defined as a probability that the observed test statistics x bar is greater than or equal to some cutoff value C, which is mu naught plus z of 1 minus alpha times sigma over root n under the, I need to write small. mu0 plus z of 1 minus alpha sigma over root n given h1. This value is just C, the critical value. So the power is probability that the observed test statistic exceeds the critical value, which is just the mean plus 2 standard deviations, given that the alternate's true. So given that the alternate's true, it's the probability of being greater than this critical value. So it's this. It's usually pretty big, like 0.08. So here's the critical value, here's the alternate distribution, it's this green area. So then, mathematically, that's equal to 1 minus the probability that x bar is less than or equal to mu0 plus z of 1 minus alpha sigma over n given h1. And then that can be shown to be equal to phi of mu minus mu0 divided by sigma over n minus z 1 minus alpha And then keep going. So that's what the power is equal to. So the power is equal to phi. Phi is the CDF of the standard normal distribution. Mu minus mu 0 divided by sigma over root n minus z of 1 minus alpha. And that's equal to 1 minus beta. And so this part's equal to z of 1 minus beta. Beta, not alpha. So if we take the inverse phi of both sides, that would give us z of 1 minus beta is equal to phi inverse of 1 minus beta, which is equal to this stuff. So taking the inverse yields z of 1 minus, keep writing alpha, z of 1 minus beta is equal to mu minus mu naught over sigma divided by root n minus z of 1 minus alpha. We solve for n, that yields n is equal to sigma squared z of 1 minus beta plus z of 1 minus alpha squared over mu minus mu 0 squared. So keep going a little bit, almost there. So sample size n equals sigma squared z of 1 minus alpha plus z of 1 minus beta squared over mu minus mu naught squared. Writing that in a little differently, that's equal to z of alpha plus z of beta squared sigma squared over d squared. So this is the form I normally see. So do all this math, and you get, it can be shown that this is equal to that exactly, actually. So anyways, if you specify the variance of the distributions, the difference, you have your null and how the minimum detectable difference that's clinically significant or meaningful or whatever. And you want to do the minimum because that'll give you the smallest sample size. The larger, the smaller, the minimum meaningful. Because if you go smaller than the minimum meaningful difference, then your sample size is going to shoot through the roof. And then you got to specify some other stuff. Let's see if this makes intuitive sense. The smaller difference you're trying to detect is, the larger the sample size. That sounds reasonable because there's more overlap, and there's more these overlapping data points you don't really know who they belong to, so they're not useful in determining if it's the null or the alternate. It's the data points over here, the data points over here that really help you distinguish which, if the null is true or if the alternate is true. And then the larger the variance, the larger the sample size. That feels intuitive. The smaller the type 1 error rate, or the more reliable you want it to be, the larger the sample size required. It needs to be same thing with the power. More power you want, the larger sample size. It all sounds pretty reasonable and intuitive. So that's sample size for hypothesis test. That's based off of power. So the sample size for the mean that I presented was derived based off of a target variance, or plus or minus some amount. And the sample size for the hypothesis test is derived based off of a power. Derive the power first and solve for n from the power formula. And now let's move on to sample size for stratified random samples. So we also have, you can calculate sample size n for stratified random samples. I'm just going to write some stuff and kind kind of explain it. So you could have something with multiple stratums, like some disease like hypothyroidism, where it occurs much more frequently in women than men, and so the incidence rate in women's much higher than in men. So it'd be reasonable to assume that you need different sample size. You'd have to sample more men to find the same amount of diseased individuals as you would for women. So you'd need probably a larger sample size of men than women, something like that. So there's sort of this generic formula that you can actually use to run a calculation, because I'm going to write all the details. This is called optimal allocation. So the sample size for a given stratum, in this, each stratum has its own sample size. And so you'd have to, if you were looking at disease between men and women, you'd have to sample so many women, have to sample so many men. They have their own rates. So anyways, for this, it's some constant K times the weight for that stratum. So stratum H, constant times the weight for that stratum times the standard deviation within that stratum divided by the cost for sampling that stratum, how much effort it takes. That's known as optimal allocation. If the costs are all the same across all the stratums, it's called Nyman allocation. And you can read up on that. I'm not going to go into details. And then some other comments are these formulas were all derived based off of the means, and also the means being normally distributed. There's also other distributions. If you're working with discrete data, a lot of times you'll be using a binomial distribution, not a normal distribution. And so there's formulas derived for that. Or you could be using a Poisson distribution or something like that. And so you obviously have to look up the appropriate formulas for your job. And there's many more formulas than what I presented in this lecture. Hope that helps.